So our next topic is integers and integer operations. And to give you some idea of what we've done to build up to this idea, we started talking about counting numbers or natural numbers, which are the numbers 1, 2, 3, and so on. And then we added in the number 0 to that set and we created the whole numbers. Well, now we're going to add into that set the opposites of all of those whole numbers. And when we do that, we have a set of numbers called the integers. We can represent the integers on a number line, and now that we have these negative values as well, our number line can extend in two directions. Keep in mind that even though we know there are numbers in between the integers, at this point we're only going to talk about integer numbers. So we're going to pretend that there are no numbers in between these numbers, even though we know that there are. So now that we have this number line that goes in two directions, we can talk about the idea of absolute value, which is the distance between a number and 0. If we want to know what the absolute value of 4 is, we're asking how far from 0 is the number 4. And since it's 4 units from 0, the absolute value of 4 is 4. Or if we asked what's the absolute value of negative 2, we'd be saying how far from 0 is negative 2. Since it's 2 units away from 0, the absolute value of negative 2 is 2. Let's look at some models for integer addition. One model is a number line model. And we'll look at this particular number sentence to see what that number line model would look like. 2 plus negative 3 equals negative 1. The first addend is 2, and we'll show that with an arrow that starts at 0 and goes 2 units to the right because 2 is a positive number. And then from the end of that arrow, we'll draw an arrow to represent negative 3. Negative 3 would be an arrow that's 3 units long but points to the left. And we end up at negative 1, which is why 2 plus negative 3 is negative 1. How about negative 1 plus negative 2? That equals negative 3. Now how can we show that with a number line model? Well, starting at 0, the first addend is negative 1. So we draw an arrow that's 1 unit long and points to the left because our value is negative 1. And then we add to the end of that an arrow that represents negative 2. That would be 2 units long and also points to the left. And where that last arrow points is our sum, negative 3. Another model for integer addition is called a charged field model or a chip model. Let's look at 2 plus negative 3. In order to represent this with a charged field or a chip model, we're going to start with a set that we're going to add some chips to. First, we'll add 2 negative chips representing the negative 2. And we will add to that 3 negative chips to represent the negative 3. And now we look at the overall charge in the field, the overall number of negative values, which is 5, which is why 2 plus negative 3 equals negative 5. When we're adding two numbers that have opposite signs, we still do the same process. In this case, we start with 1 positive chip for the positive 1, and then we add to the field 2 negative chips. Now, an important rule of the charged field model is that when we have a positive chip and a negative chip that we can pair up, that's called a plus-minus pair, we know that they will sum to 0. So, in essence, we take that plus-minus pair and we remove it from the field. And that leaves us with 1 negative chip, which is why the sum is negative 1. Here's an example of a book publisher's version of the chip model. They're using virtual chips in order to model integer operations. This is from Holt, Reinhardt, Winston. So let's say we wanted to look at 1 plus negative 2. We would put one positive chip to represent the 1 and two negative chips to represent the negative 2. And then to show that those plus minus pairs add up to 0, we can drag a negative chip onto a positive chip and it will disappear. It becomes nothing, and we're left with negative 1. Here's another example of using a charged field model for addition. Let's say we wanted to find out what negative 3 plus positive 3 is. We'd start with 3 negative chips to represent negative 3, and then we would add to the field 3 positive chips to represent positive 3. We've got 3 plus minus pairs that sum to 0. And what we're left with inside the field is nothing. In other words, we're left with 0. Now that's an example of additive inverses. Two numbers are additive inverses if their sum is 0. So we've just shown that negative 3 and positive 3 are additive inverses. The charged field model can be used for subtraction as well. We need to remember that subtraction is take away. So when we're dealing with these chips, we're going to be thinking of taking something away. Let's start with negative 2 minus negative 1. Now our field's going to start with 2 negative chips to represent the negative 2. And then we need to take away from that 1 negative chip. What we're left with is 1 negative chip. So negative 2 minus negative 1 is negative 1. Now obviously I could literally take the chip away through the magic of PowerPoint. How are you going to show that when you're writing this on paper? Well, you're going to start with the 2 negative chips, and then to show that you're taking one away, you can just draw a circle around what you're taking away and then an arrow that shows that that chip would be removed from the field. That would leave you with the negative 1. How about 1 minus negative 2? So in this case, the 1 means we're starting with 1 positive chip. And then we're subtracting from that negative 2, which means we need to take away 2 negative chips, but we don't have 2 negative chips in the field. So this is where those plus minus pairs are going to come into play again. We can add into the field as many plus minus pairs as we need, because a plus minus pair is simply a 0. So we're adding 0 back into the field. We can add as many of those plus minus pairs as we need so that we can take away the 2 negative chips. And when we take away the 2 negative chips, what we're left with is 3 positive chips. So 1 minus negative 2 is positive 3. Let's look at that same problem using the virtual chips. We had 1 minus negative 2. So we start with 1 positive chip. Now since I want to subtract negative 2, I'd like to take 2 negative chips away from this, but I don't have 2 negative chips. So what I'm going to do is add in 2 neutral pairs so that I have 2 of those negative chips to take away. Now I can subtract the 2 negative chips, and that leaves me with 3 positive chips. So 1 minus negative 2 is positive 3. Let's try one more subtraction problem with this charged field or chip model. Negative 2 minus 1. So the number negative 2 means we're starting with 2 negative chips. Minus 1 means we're taking away 1 positive chip. But we don't have any positive chips to take away. So we'll add to the field plus minus pairs until we have 1 positive chip in the field. And now we can take away that one positive chip, which would leave us with 3 negative chips. So negative 2 minus 1 is negative 3. We can also represent subtraction with a number line model. We'll be using arrows just like with our other number line models. But we have to understand that negative numbers will have arrows that point to the left, and positive numbers will have arrows that point to the right. Now the direction of the arrow will be indicated by the operation that we're using. If we have subtraction, we will be reversing arrows. And if we have addition, the arrows will be the same direction that they started. So let's take a look at negative 2 minus 1. Starting at 0, we're going to draw an arrow that represents negative 2. So that would be an arrow that points to the left 2 units. From the end of that arrow, we want to subtract 1. Now an arrow that represents 1 would be an arrow that points 1 unit to the right, but the subtraction is going to reverse that. So subtracting 1 would be an arrow that points 1 unit to the left. So negative 2 minus 1 is negative 3. How about negative 2 minus negative 3? Well, starting at 0, we draw an arrow 2 units to the left to represent negative 2. Then we think about what a negative 3 arrow would look like. It would be an arrow that starts at where the negative 2 arrow ended and would point 3 units to the left. But we're subtracting it, so we have to reverse that arrow and make it point 3 units to the right. We end up at 1, so negative 2 minus negative 3 is positive 1. Now these statements are actually related to addition statements. We said that there was a relationship between subtraction and addition. In the first case, negative 2 minus 1 is the same thing as negative 2 plus negative 1. And if you look at the number line model, you'll see that that's exactly the same picture we would have drawn for negative 2 plus negative 1. And in the second case, negative 2 minus negative 3 is exactly the same as negative 2 plus positive 3. The number line model looks identical in both of them. So what we've got is two examples of relating subtraction and addition, which is that if we are subtracting two things, a minus b, that is the same thing as a plus the opposite of b. And quite often students find that it's easier to think of integer subtraction in terms of integer addition. So they find it easier to change subtraction problems with integers to addition problems with integers. So moving on to our next operation with integers, multiplication. We can use a charged field model, a chip model. So let's think about something like 3 times negative 2. Now we thought about multiplication as repeated addition, and that'll be helpful here. 3 times negative 2 means we have 3 groups of 2 negatives. So we're going to add 3 groups of 2 negatives to our field, and we end up with 6 negative charges. So 3 times negative 2 is negative 6. If the first factor is negative, then instead of adding 3 groups into our field, we can think of it as taking away 3 groups of 2 positives in this case. Now if you think about what the field looks like, it doesn't have any charges in it, and we need to take away 3 groups of 2 positives. So we can use that idea of the plus minus pairs again. We can put in enough plus minus pairs so that we can take away 3 groups of 2 positive charges. So we can take away 1, 2, 3 groups of 2 positive charges, and that leaves us with 6 negative charges, or negative 6. There's also a number line model for multiplication. Remember, we talked about the directions that the arrows go to represent positive and negative numbers. So if we have 3 times negative 1, that means we have 3 groups of negative 1 arrows. So we would have 1, 2, 3 groups of negative 1 arrows. So 3 times negative 1 is negative 3. Negative 3 times negative 1 means we have to reverse 3 groups of negative 1 arrows. So that is a negative 1 arrow, but reversing it means it has to point that way. And we need 1, 2, 3 of those to end up at positive 3. So let's look at some patterns that we can see in integer multiplication. And we'll start with positive values. So positive 3 times positive 3 is 9. And 3 times 2 is 6. And 3 times 1 is 3. So the pattern that we're seeing on the left side of the equal sign is that that second factor is decreasing by 1. And on the right side, we're seeing that the product is decreasing by 3. So that leads us to 3 times 0 is 0. Now if we continue that pattern, and on the left side we decrease the second factor, and on the right side we decrease the product, we're going to be able to see what happens when we have some signed values, some negative values as factors. So the pattern on the right side is we seem to be subtracting 3 to get from one product to the next. So our next multiplication problem would be 3 times negative 1. And continuing the pattern on the right side, subtract 3 from 0, we get negative 3. And we can continue the pattern, so 3 times negative 2 would have to be negative 6. And 3 times negative 3, continuing the pattern on the right, would have to be negative 9. So we're going to take that last statement we had, 3 times negative 3, which we said was equal to negative 9, and we're going to build off of that. So if 3 times negative 3 is negative 9, 2 times negative 3 is negative 6. And 1 times negative 3 is negative 3. And we know that 0 times anything is 0. And if we look at the patterns, we'll see that the products are increasing by 3. And on the left side, the first factor is decreasing by 1. So the next multiplication problem would be negative 1 times negative 3, and continuing the pattern on the right by adding 3, that would have to equal positive 3. And if we continue these patterns, we'll get some more multiplication facts that involve multiplying 2 negative numbers together. So let's take a look at what's going on here. The first 3 problems we have involve a positive number times a positive number, and the result was positive. The next 3 on the left side that involved 2 numbers with signs show us that a positive number times a negative number is giving us a negative value. On the right side, we can see that a positive times a negative is a negative, and that a negative times a negative is a positive. So if we take a look at which number patterns gave us positive results, that was when the signs were the same of the two factors we were multiplying. And the ones that gave us a negative result were when the signs of the two factors were different. So that's how we've got sign rules for multiplication that we can demonstrate by looking at number patterns. Now we know that there's a relationship between multiplication and division. If we're multiplying A and B and we have as a product C, that means that C divided by B equals A. So for example, 3 times 4 equals 12 would mean that 12 divided by 4 equals 3. So how can we use that to think about signs for integer division problems? We know that a positive number times a positive number will always give us another positive number. So that means that a positive divided by a positive is always going to be positive. We know that a positive times a negative will give us a negative result. So that means a negative divided by a negative would give us a positive result. And since a negative times a positive equals negative, then we know that a negative divided by a positive is going to equal a negative. And finally, a negative times a negative equals a positive, so that means a positive divided by a negative would have to equal a negative. So what we see is that the sign rules for division are identical to the sign rules for multiplication. So one last thing to talk about, and that is a nice little number pattern that we can see when we multiply certain numbers that fit into a difference of squares formula. Now we've already talked about the difference of squares formula. We've developed it with patterns, but now let's see how we can actually use this to multiply certain numbers. Let's say we want to multiply 42 times 38. Now what's important about 42 and 38 is that if we look for the number that's exactly in between 42 and 38, that's a very friendly number. It's 40. So that allows us to rewrite 42 as 40 plus 2 and to rewrite 38 as 40 minus 2. And once we do that, we can see that we've got that same number pattern that exists in our difference of squares formula, where 40 is acting like the A and 2 is acting like the B. So that means we can rewrite this as 40 squared minus 2 squared. Take a look at the right side of that difference of squares formula. A is 40 and B is 2. And since 40 squared is 1600 and 2 squared is 4, that gives us two numbers that are very easy to subtract. And we get a result of 1596 for our product. Look at one more example of this. Now remember, this only works when we have two numbers that have a number right in between them that's a friendly number. That would be a number that ends in 0. So if we want to multiply 107 times 93, we're in luck because there is a friendly number exactly in between 107 and 93. That's the number 100. That lets us rewrite 107 as 100 plus 7 and lets us rewrite 93 as 100 minus 7. Now we've got something that's fitting into this pattern for difference of two squares, where A is the 100 and B is the 7. So that means we've got 100 squared minus 7 squared. 100 squared is 10,000 and 7 squared is 49, and the difference of those two is 9,951. So that means that the product of 107 and 93 is 9,951. So that's a quick look at integers and integer operations and some models that we can use to demonstrate all of those operations.